Hi, welcome to lesson 14C, Rates of Change. The goal of today's lesson is to learn how to calculate rates of change of curves at specific points. So the key there is to learn how to calculate rates of change of curves at specific points. So we've looked at rates of change in the past, and rates are basically comparisons of two quantities that have different units. So we could be comparing dollars per hour if we're talking about somebody's salary or wages for hours worked. We can talk about kilometers per hour in the change in distance that somebody drives or walks or runs over compared to a certain number of hours that they're traveling. Dollars per kilogram could be the cost of produce or meat at a butcher shop or something like that. Then we get into liters per 100 kilometers. That could be the gas mileage for a car. People per square kilometer could be the area or the number of people per square area for the house. Sorry, not per house, for living area in the country. Goals per game, etc., etc., etc. So there's all kinds of different rates that we can be looking at. One of the more common types of rates that we look at is speed, which is the rate of change of distance over time. So speed is the rate of change, the change in distance over the change in time. And that will give us the speed. Usually, like a lot of times, it'll be in meters per second, or it could be in kilometers per hour, maybe miles per hour. It just depends on the units that we're dealing with. Now that's all fine and good if we're talking about a linear graph. We can do that fairly easily. If it's linear, then we can take a look at this is the distance in kilometers, and this is the time in hours, for example. We could then look at the change in distance. So the change in distance is the vertical portion of this, what we call a rate triangle. And here is the change in time here. And to get the rate of change along this, the rate of change or the speed would be then the delta distance over the delta time, which is the speed, so kilometers per hour. Okay, so that's all fine and dandy. Where it gets a little bit more complicated is when we're talking about curves. And curves, if we're looking at some sort of a curved thing, and I'll look at this in a little bit. Sorry, we'll look at this soon. The curve, we'd have to sort of look at a point of tangency and then look at using the tangent to the curve. We'd be looking at then the change in distance over the change in time for a tangent to the curve, and then that gets a little bit more complicated, but we'll take a look at that with more detail in a moment. Okay, so now what I'm going to do is I'm going to take a look at a curved function, and we'll see how all this kind of pieces together and how calculus gets formed here. So basically, when we try to find the gradient of a line, we need 2 points. So let's just say, for fun, I'm going to go here. This is x equals 3 here. So I use this. This is just some function. I just drew a curve, and so I'm going to say that this point right there, because that's x equals 3, this point is actually 3 f of 3. Okay, so this function is y equals f of x. I'll just label this up here, y equals f of x. And this point, of course, then would be 3 f of 3. So the y value of this point is calculated for f of 3. So in order to find the gradient, suppose I'm going to use this point as my key point, and I'm going to draw a secant here. So the way to get the gradient of the secant is to use this point, and then of course this point up here. And this point, I don't know exactly what that is at the moment, so that's going to be some point x, f of x, of course. And what I'm also going to then do is I'm going to say, well, this x value up here is some horizontal distance, and I'll just draw a little guideline down here. So that x distance, or that x value, is some horizontal distance away from the x value of 3. So from here to here is some horizontal distance. So because it's some horizontal distance, let's just call it h for the horizontal distance between x equals 3 and this value of x. So now what we can do is I can redefine this and say this, instead of just x, I'm going to say this is now 3 plus h. Okay, because it's the x value of 3 plus this horizontal distance h. So the x coordinate of this point is now 3 plus h, and the y coordinate of this point is f of 3 plus h. Okay, so the notation is getting a little bit more complicated now, but it's 3 plus h and f of 3 plus h as the x and y coordinates of that point. Okay, so now in order to find the gradient of the secant, I'm going to have to use these 2 points, and the gradient can be calculated as m is, from what we've seen in the past, y2 minus y1 over x2 minus x1. And I'll put in f of 3 plus h as my y2. So it'll be f of 3 plus h. And then I've got f of 3 down here as my y1. So I'm going to subtract f of 3. And that's going to be divided by, so this is the delta y, or the y step. And for the x, the delta x, well, the x value is 3 plus h for x2, and the x1 is 3. So down the bottom, x2 is 3 plus h, and the x1 is 3 from down here. Okay, so I can simplify this denominator quite easily, 3 plus h minus 3, and this is, just to confirm that, this delta x. So I'm just going to clarify that that's the delta x, and so the numerator is f of 3 plus h minus f of 3, and that's going to be all over, now that we simplify the denominator, that's all over h. Okay. This thing that we're working with right now, that's called the difference quotient. And the difference quotient is, well, it's a quotient, which is a rational function. It's a quotient, the division between two functions, and the difference is right here, the subtraction of the numerator. Okay, so it's the difference between these two functions and divided by this value of h, which forms the quotient part. So this is now the difference quotient that we're going to be using. And so what I'm going to do is, it'll be more useful when we see what that actual function is that we're using here. When we can actually substitute the 3 plus h into an actual function and do some simplifying. But this is just the general gist of things. What I'm going to do now is, instead of having h so far apart, so I've got this x value here is 3 plus h, this x value here of 3, and this is a pretty large distance of h here. What I'm going to do now is I'm going to take this point, I'm going to slide it down the curve to about here. Let's go right here. Okay, so now this secant then becomes a little less steep. So now I've got a second secant here, and it's going through this original point of 3f of 3, and now it's going through this new point, which is still 3 plus h, f of 3 plus h. The only difference is now I've changed the size of h. I've now moved h to here. So now h is just this size. It's a lot shorter. So this is now gone. So now the h distance, the horizontal distance between those 2 points, is much smaller. Okay, so I'll do that. Then what I'll do is I'm going to further slide this point down the curve, down to around here. And that point is still 3 plus h, f of 3 plus h, because it's still the function of the x value. And the x value is still 3 plus this horizontal distance. Now the horizontal distance is become much smaller, so now it's only here. So this is gone now. So the horizontal distance is just here, and the secant is now still through this point 3f of 3, but now we see that the second point is much closer. So still, again, we've got 2 points. We can still use delta y over delta x. We're still using this delta y, and 3 plus h minus 3 still just leaves us with the h. Now we see, as we're going through this process, that this horizontal distance, this h value, is getting smaller and smaller. And we can do it again. We can slide this even further, closer down towards 3f of 3. We still have a secant. Okay, but now it's getting a little bit harder to distinguish between the secant and the curve. So again, still this is 3f of 3. This now, well, of course, it's still 3 plus h, f of 3 plus h. And now we see that this h, this size of h here, is getting even smaller still. Sorry about that. This size of h, this horizontal distance now, is still h, but it's getting much smaller. So we're going to continue this process until this point is so close to 3f of 3, or to the value of 3, that h is actually going to approach 0. So here comes our talk about limits. Okay, so we talked about limits in the past couple of lessons. Now we're going to be looking at this gradient here, the gradient, which is the average rate of change, because we're using the 2 points and we're finding the average. The gradient is going to be the limit now of f of 3 plus h minus f of 3 all over h as h approaches 0. Now we can't divide by 0 because that's undefined. However, h can become very, very, very close to 0. And this is where the whole idea of calculus comes from. We're trying to find the gradient of the tangent. Now we can't find the gradient of a tangent because there's only 1 point on the curve. That's why we still need those 2 points so we can find the delta y between those 2 points. And that's why h cannot equal 0, like the distance between the 2 points, the horizontal distance between the 2 points cannot equal 0, but it can approach 0. Okay, so then as we find the gradient of these different secant lines, we'll start to see that the gradient of each of those secant lines will begin to actually imitate, or it'll become very, very close to the actual gradient of the tangent line at the point of tangency, which is 3f of 3. Now when we do all that, we can do the same thing from the other side, and we start from over here. Again, here is 3 plus h, f of 3 plus h, and the secant goes from our key point, 3f of 3, right here, through this point, which of course in this case is the origin, but doesn't really matter. Now in this case, because this point, this x value is less than 3, less than the target x value here, we still have this horizontal distance of h. Okay, we still have that horizontal distance of h, but in this case, when this point is to the left of 3, this case, h is less than 0. So we're actually going to have a negative value. Over here, h was greater than 0 because we had a positive value because the x values were positive and greater than 3. Over here, the x values, well, they're still going to be positive, but they're going to be less than 3. And that's because h is less than 0. So 3 plus some negative value will then put this x value of this point less than this x value here of 3. And then of course the same sort of idea, we're going to slide this point up the curve, thus forming a shorter h value here. So this part's gone, so we just got a shorter h value. This point is still 3 plus h and f of 3 plus h. And now the secant goes from, again, still from this point of 3 through this new point. And so it's becoming a bit of a mess here with all these secant lines or whatever. But we're going to slide this point closer and closer, closer up to 3 now from the left. And we're going to get that point so close that again, h is going to be approaching 0, but this time it's from the negative aspect. Okay, the same sort of idea, we can do the same calculations, and as we go, we're going to see that the gradient of all of these secant lines to the left of this key point of 3, and all these secant lines to the right of x equals 3, all those secant lines are going to begin to zero in on one gradient, which is going to be the gradient of the tangent at 3f of 3. Okay, so this one will start to become steeper. These secants will start to become less steep, of course in this example. And then if we were to take the average of the two closest gradients of the secant lines, that would be our approximation of the gradient at that point of 3f of 3. Okay, so that's basically what we're going to be doing when we look at the investigation tomorrow. We're going to look at a couple of investigations in class, and this is what we're going to see, and this is our sort of next logical step into the realm of calculus. Okay, so that's about it for now, but we'll take a look through the investigations tomorrow in class, and hopefully things will become much more clear once we start using actual functions as opposed to just the function notation. Okay, so thanks for watching, and we'll see you in class.